All right, I'm now going to introduce our speaker. So, Keri has been a summer RA here at Topos for the last many weeks, and she has a couple more with us. I've been having a great time doing research with her, and she's going to tell us a little bit about some of that research and tell us about composing instantaneous machines. Take it away, Keri.
Okay, so today's talk is going to be on, on composing instantaneous machines. So before we get into that, we're going to first just recap the definition of a Mealy machine. So a Mealy machine has a set of states S. It has I, which is an input alphabet. And it has O, which is an output alphabet. And so this comes with a structure that takes S cross I to O cross S. And what this gives is two functions. So it gives some sort of readout function, which goes from S cross I to O. And it gives an update function, which goes from S cross I to S. And so what this says is if I have a state and I give an input, I get an output. If I have a state and I give an input, I get some next state. And so how this differs from Moore machines is that in a Moore machine, we just have R, which goes from S to O. So there's no dependency on the input alphabet. And so what we want to do with this is we want to extend what was done for directed wiring diagrams, which has this readout approach, and we want to be able to now have this dependency on the input alphabet. So before we get into what we're going to call dependent directed wiring diagrams, we'll first go over just directed wiring diagrams. So DWD for directed wiring diagrams. So this is an operad, so a symmetric monoidal category, and what it has is it has objects that are of this form, where X in and X out are sets. And we can view this by looking at some sort of object which has input ports X in, output ports X out. And then for morphisms,
Keri, are you going to require yourself to always put the inputs at the top? Like, is that going to be a thing that you're...
Yeah, that's how I'm drawing it, yeah. And so for morphisms, it's going to be some F which goes from X in, X out to Y in, Y out. And how this looks is we have these sets of wires. So we have W in, which has source Y in, target X in. Then we have W wires, which go from X out to X in. And then we have output wires, which go from X out to Y out. And so visually, we can view this as if this is X in, this is X out. And so we can have some input wires like this, which go from Y in to X in. We can have some W wires, which loop back up from X out to Y in. And we can have some output wires, which go from X out to Y out. And so we can study this semantically by looking at an operad algebra, which is a functor from DWD to set. And how this functions is on objects. It will map to the set, which has, yes?
How do you compose these things? Or is it obvious how you compose?
Oh, just by, so pull back, yeah.
What is the monoidal product?
plus, yeah. So it will be x in plus x. So the coproduct, yeah. Okay, and so this will get set of states S, and it'll give a U and an R. And in this case, the U goes from RS cross RX in to RS, and the R goes from RS to RX out. And then on morphism, so if we have some F, which goes from X in, X out, to Y in, Y out, then this maps to some set function S U R, and we'll call it now U prime R prime. And so now U prime has type RS cross RY in to RS, and the readout prime has RS to RY out. And so these are defined. U prime will go from RS, oh, okay. So recall when we have some set function, if we have A to B, we can get some F star upper, which is going to be FA to F.
R to the A? Or
R to the,
just F to the power A?
oh, I was just saying if we have a set function, and then you can do this by taking the,
What does FA mean?
it's not, it's R.
And RC, RA?
Yes. Wait, is this the wrong order?
Yeah. So
This is sub.
we'll go backwards.
Okay.
Wait, is R just the reals?
Yes. And so we're going to use this notation. So if we take, we can get a function from Ry in then to Rx in. And we're just going to denote this by W star in, which is just going to be a composition of T star, S star. And we're going to denote this one by W star. And then this one,
Does F lower star add stuff up?
yes,
Okay.
the inverse. It adds up everything that mapped to it, yeah.
Okay.
And then, so we're just going to use this notation. And so then we can get RS cross RY in. And we take the identity on RS, and if we do W star out, we now have something of the form RS cross R X in. And so on this, we also need to not only get what's inputted from these wires, but what's inputted from X out. So we want to diagonal on the RS. So we get RS cross R X in, and then we can take the readout function and get an output from the original. And so we'll get RS cross RX in, which gets us RS RX out, cross RX in, and now we want to loop back up. So we can take RS cross W star cross RX in, which gets RS cross RX in, cross RX in. And then because of this, we want to add these two coming in together. So we're just going to take addition on these two inputs. So addition, and now we get RS cross 1 RX in. And then we can do the regular update function. That was what we were mapping from. And we'll get RS. And the R prime is a lot easier because the R prime will just go from RS. We can go right to RX out. via R. And then all we do is feed that then down into the y out. So we get w star out, ry out. Yes?
So when the reals enters the picture, is the idea that like the Mealy machine I/O is going to be R to the X in
Yes.
and R to the X out? And are you using are you using anything besides R being an abelian group to do it? Is there
But
something
this was on yours. Okay.
or just a regular old monoid? Commutative monoid, yeah.
Okay.
So
Yes.
this say, so you said amorphism UR to U prime R prime is present if it turns out that U prime is this composition and R prime is that composition?
So this is saying I'm taking some element of this S, so SUR. So I'm taking some semantics on a machine.
Yeah, inside of the value
Yes.
of the algebra, right.
And then this is what it gets when I map it.
Sorry if I missed this.
No, you're good.
Are you saying that any functor from DWD to set will have this?
This is a particular functor.
Okay,
Yeah, yeah.
These are special functors.
Yes.
And there's one for each S, right?
Yes, one for each, yeah.
Just what does it mean when you write like a type on the name of the map? Where like the name of the map is labeled with like
Oh, this is what I'm doing. So I'm saying RS, this is just the identity. And then I'm saying apply W star out, which is a function from, did I do that? Apply W star, oh, this is W star in. Apply W star in, which gets me from RY in to RX in.
but why RS cross W star in?
I'm just doing it on each component.
Oh right, yeah, I see it now. Yeah. Great.
Maybe I was a bit lost at the what exactly are the W's? Yeah.
So these are wires. So this represents, like in this case, this is some F. So these two are part of this set Wn. And S gives the source. So this one has this source. This one has this source.
So the data of morphism consists of these three W's, the Wn,
Yes.
middle W, and the WL.
Yeah.
What does this algebra mean? So like S is going to be a state space and a like.
RS is a state space. S is a set of states. Yeah.
Is it, so is there like a picture of electricity flowing I'm going to imagine in my head when I think of a particular element of f of x and x out or anything?
Wait, I'm not 100% sure what you're asking.
Why this? How did we decide to write down this algebra? What does it feel like?
Well, this is, I mean, so again, so you're going to take some value on your states, and if you give it an input, it's going to, I mean, you can either do it continuous or discrete, and it's either going to transition to a next state or it has a vector. And then this is going to be, at some state, this is the output of just how it's the value of the output.
Yeah, that helps.
Okay. Yes.
So going back to the directed line diagram.
Yes.
So a composition of two morphisms, a picture of that would be three nested boxes.
Yeah, so,
And
yeah, so it would have another one, and we can have now W prime, which can go this way. Yeah.
And so I'm just trying to visualize what in that composition, what's the role of those feedback arrows in the middle box? Like,
So in this box,
yeah, so in the middle box, like
yeah,
in the Y,
okay.
yeah. So you just drew like an arrow going from its outputs to its inputs. So what does that connect to? What role does that play in the composition? I'm just trying to see what the picture looks like.
Okay, so these, if I now have another like Z out, Z in, so these stay, but I also can now have, here we see these two compose because they have the same source and target, and then, so I have now two sets of loops, but when you compose them, they just become, we write it as like W plus W out cross, oops, this is Y out, W prime cross W in. So we just add them. Yeah.
So if you go from x out to y out, loop back around to y in, and then come back to x in.
This
that
is another,
is
yes.
logic,
Yeah. Yeah, yeah.
Oh, I see. Okay, great. Thank you. Yeah. Yes.
What worries me a little bit with feedback is, does it happen instantaneously, or is there some time step that
So in
values are moved one at a time?
So I think it's going to be different in the case of Mealy. So this has no dependencies. We haven't gotten to dependent yet. So it's just going to have one feedback from whatever the state is, because it has a readout, and it'll give you the output, and it just add them together, and you're done.
You're saying that we're in more machine land right now.
We're in more machine land right now.
So there's feedback, but it's not instantaneous.
Yes.
And your point is to get us to
Yes.
instantaneous. Yeah. So your point is to deal with Dana's worry.
Yes.
The whole point of this talk is.
Yes.
Okay.
Okay, so now we can start looking at a new category, or a new operad, for dependent directed wiring diagrams. Okay, so what do we want these to look like? Well, we want them to have this type of structure. So we do want some x in, x out. But we also have an additional thing here, which is dependency, because I can now have my output depend on my input. So here's one example I could have. I could have this output depends on what I input here. This output depends on what I input here. But I can also have something like this, which is a different dependency. Now this output depends on this input, this output depends on this input. And so we want to distinguish these two. So what we want to do is we want to have something where we have objects that look like this. Additionally, we want to keep track of the dependency. But this is a different object. And so we need a category for this. So this is pretty reminiscent of the growth and deconstruction of a functor. So we'll just give that definition.
Sorry, an object is labeled by a box, and then that same box with something in it?
Yeah, okay, so technically we want to have this as a first component, some object in DWD, and then we can call this d of x. So if w, we're going to say wx equals a set of all dependencies, which is these. On x in, x out. And then d of x is an element of wx.
And dependency is a relation.
Yeah, so dependency is a relation between the input and output. And so the growth and deconstruction of a functor. So this has to take in some functor f, which goes from some category to the category of all categories. And we want to take this equals the growth and deconstruction of f. This is how we denote it. And so this has objects of the form xc, where x is an element of, is some object in C. C is an element of, oh, is that?
The choice of letters is just a little scary.
Wait, what do you want me to do?
C seems like it would rather be an object.
That is true, yeah. Okay, we're going to do Cx. Okay, such that C is an element of an object in C, and X is an object of f of C, which is some category. And then these have morphisms. So we go from C1, X1 to C2, X2, which is some FG. And here F is a morphism in C. And then we have G, which goes from F of X1 to X2, which is in F of C2. And so to get something of this form, we want our C to be DWD because this is what these objects are coming from. And we need to get some subcategory of cat. And so what we want to do is actually make cat be the category of posets. And we want to map this as follows. Okay. So if we have some x in, x out, we want to define, so we're going to call this is a functor. We're going to call this W, and we want to define a functor DWD to poset. And we want to map this to really the set of all dependencies on here, but we need to give it a poset structure too. So we're going to map it like this. Where this dependency is less than or equal to this dependency because it's a subset of it. And so this is how we're going to give x in, x out, the dependencies on it, a poset structure. Yes?
Should you have like one input and two outputs? So on the right, it seems like you have one input and two outputs. But on the left,
Yeah, we're going to do this, yeah. And so this, now we need to define it on morphisms. So let F be a morphism in DWD. And so this now, we can draw it. So if we take, let's say, some dependency here, and let's have, this is x in, x out. And now we have some y in, y out. So let's give so this now is going to be equal to, this is just an example. So we have two inputs, one output, and we have, this is the one dependency we have, so we then end up getting a dependency like this in y in, y out, so we just compose them because here we have a dependency, well, what is this input? It feeds in from this input. And so how we want to actually define that is we want to say, well, here is some d of x, which is some example of a dependency on x in, x out. So we need to say w of f of d of x. So we need to get some d of y now. And so what we want to say is, well, we have to take w in. We need to compose it with d of x. And then with, we could have to compose, okay, so we could then go just w out. But we also could have the option of going W in cross d of x cross W cross d of x cross W out. Because if there was some dependency here, we would have to go here, here, here. And we can do this, I mean, in this case we don't, but we could do this n number of times. So we'll write it like Wn cross d of x cross Wx, no, W to the n cross d of x cross W out. Because these are all the dependencies that can form, yeah.
I think I'm a little bit losing something, the track a little bit. My understanding was that somehow Mealy machines are fine with feedback as long as like the feedback doesn't touch something where there's a blue line. That's what in my head I was thinking.
Okay, so yeah, we're gonna get to that in 2 seconds.
Okay.
Wait, did I make a mistake here?
You might not have.
Okay.
I wasn't sure like how you knew what a valid F was. I thought somehow
Yeah,
valid Fs were somehow going to be involving the blues.
They are.
Or something. Okay.
Yeah, so I'm gonna create this category and then I have to get rid of some morphisms.
I see. So currently F is just any old F.
F is any old F.
And you're not
I
caring
just
about the
made one
thing,
that
and then
didn't have
we're
a
gonna worry
problem.
about the
Yeah.
problem in a second.
Yes.
Okay. Thanks.
Okay, so this is going to give us, okay, so this is now defined on morphism. So now,
And I don't want you to adjust it, but those products are really some kind of pullback, right?
yeah, I should have
Don't decorate.
like X in, yeah. And so now we have this functor, and we can define int over bar W, which is the growth and deconstruction of the functor W. Okay, but now this category is not exactly what we want because we can have a problem. I have a good example. Okay, so consider okay, so consider this example where the inside gives how the states update. And so, okay, and so now this gives, we do have a dependency here to here because this output depends on what I input, this output depends on what I input. But the problem with this is if I want to get this output, which is yt plus b, I need to know the input. But the input is what's feeded in from this output. If I want this output, I need this input. This input is, again, what's feeded in from this output. So this is unsolvable because I have a cycle. So what we want to do is we want to take this category and remove any morphism that forms a cycle. So a cycle precisely is given, so we see this is coming from, if we tensor these together, this is coming from W, and these are coming from some d of x. And so a cycle is really some element in d of x, tensor x out, not tensor, pull back, W, and then x in, and such that the source of C1 equals the target of C2n. And so this is coming from the dependency, and this is coming, so this is some dependency. This is coming from the F, which is the morphism between the two DWDs. And so what we want to do is we need to remove these from the category int. So let's say we have some okay, so let's say, so I'm going to not keep writing G because the second morphism is going to be a morphism in a poset, so it's just going to be the unique one less than or equal to. So let's say we have some morphism in here such that when I look at F, I can have some element of here that forms a cycle. So I want to remove this morphism from the category, but I want to keep these because there's definitely going to be morphisms between them that are fine and are not going to form cycles. So we want to take a wide subcategory, and we're going to call it DWD for dependent directed wiring diagrams. And this, again, it's wide, so it has all objects x in, x out, d of x that are in the growth and deconstruction of bar W, and the morphisms, so all in int W that don't contain cycles. And this is a category because if you take some F less than or equal to and G less than or equal to that both don't form cycles, then when I compose them, I also cannot get a cycle.
Sorry, I missed what less than or equal to refers to.
So less than or, no. So less than or equal to, I was saying, so if you look in the growth and deconstruction, I'm going to have, these are my morphisms. In here, but it's a poset, so I was just denoting it by the, yeah.
The relation is a subset of that relation.
Yeah. Yes. Yes. Okay, so this is going to be our category D, our operad. Oh, this is going to be our operad dependent directed wiring diagrams, and it's going to be symmetric monoidal because, why is this? Okay, so we used a paper that showed that if this was a lax monoidal functor, then the category is symmetric monoidal, and this subcategory is going to follow as also being symmetric monoidal. And so now we want to do the same kind of thing and create an operad algebra that gives us the dynamics of dependent directed wiring diagrams. So, yes?
Can I ask about like this unsolvable thing?
Mm-hmm.
So how does that work? Is it a morphism? Like,
So it is a morphism in here, but I don't want it when I'm looking at dependent directed wiring diagrams, because then when I go to create the dynamics, I can't do anything.
have something like from y out to, is it x in?
Okay, so just think about this as once I tensor it, I can have a x t. Yeah, so
Okay.
then I just go back up here.
I see.
Yeah. Okay, so
Can I just paraphrase where we're at? You're like, I want to compose these things called instantaneous machines. I care about dependency, so now you've constructed the like, instead of DWD, you're now going to use DDWD. And now you're about to be like, now let me show you how we could like plug in the Mealy machine.
yes.
That's the kind of thing.
So we want to create an operad algebra from dependent directed wiring diagrams to set like was done for DWDs. Okay, So now let's define on objects first, which is the easier one. And so let's say we have some object in D, D, W, D. So I want to map that to a set. Again, we have some UR, but now we have a restriction on this R. So U again is going to go from RS cross RX in to RS. And then R is going to go now, instead of just RS, it's going to go RS cross RX in to RX out. And this also has to satisfy, let J be an element of X out. So if J is some output port. So I want to say R of J. So actually, let's write. So we have some dependency. We can think of these as wires. This is a set of wires that has source X in and it has target X out. And so what we want to say is we have R of S. We just want now the output on R. So it's just going to be R to the J, which is just R. And we want to say we'll take the inverse image of J, which gets us a set of dependencies that have target. And then I want to apply the source. So basically, this is showing that this output port can only depend on what's coming from these dependencies. And so now we can do it on morphisms.
Are these R's of J's extra data?
No, it's what forms this.
Okay.
So let's say we have a morphism in D, D, W, D. And so now we're going to have, when we map that via dynam, we're going to have some set function. So we want to take some SUR that has this type, and we want to map it to an SU prime R prime such that now U prime will have RS cross R Y in to RS, and R prime will have RS cross RY in to RY out. And so before on just directed wiring diagrams, you just had to add whatever R gave on the output and whatever was coming in from Y in. But here we can have some differences. So consider this morphism F, which goes from where this is a dependency on X in, X out, and this is on Y in, Y out. And so now what we want to do is we want to say, let's look at the update. So we want to say, okay, well, now I'm inputting something in Y in, I need to bring it down to X in. So now I have RS cross RX in. Okay, and again, I want to take this diagonal of, oh no, I do not want to take a diagonal. Okay, so here, the thing is, if I input W star let's say I have some input A, and now it becomes W star in A. It becomes input in X in now. So if I now take the readout, I now get some, let's say, R W star in A S. So I now need this in my readout function where before I didn't. So let's say this gets some output O. Okay, well now I have output O, and like before, I want to bring that back up to get some X in. So I want to say W star in A plus W star O. So now I have the input. I added it in with the W star in A. But the problem is now I just updated these two input ports. So now my output is going to change on them again. So I actually need to take the readout of this again in my state S, and I'm going to get new output. Okay, but now this comes back around here, so I now just updated this again. So now I have X in, let's say this is O prime. But now this also has a dependency here, so I just updated the output one more time. So now I have to bring, do I have to bring that back up again? No, I just updated this. And so eventually in finite time, I have no cycles in this thing. So in finite time, in n steps, I'm going to finally stabilize my input and output. So what we want to do is we want to say, let phi given r, a readout function on x in, x out, and some input, and in this case it's W star in A, and some state S. So I want to say, given an input and output, I now want to do W star O plus W star in A, and the readout of the input at S. So this is coming back around, and this is reading out what was inputted into the machine. And so we want to get the fixed point of this. Because at that point, we can no longer update the input anymore, and therefore the output is stabilized, and I can just go back down to get a Y out. And so here, because we took in a state and an input, we can say we'll take the fixed point of phi, and I'll now get some Rx in, Rx out, which has finished updating, but I should have, whoops, sorry. We also want to not take just RS. We want to triangle this because we need two RSs. And so then this is another RS. And so now we only care about the state we're in plus the input that's stabilized. And we can take the regular update function from RS cross Rx in, and we get a new state. And so we want to keep this fixed point here. And we want to do the same thing for R prime. So we want to go RS cross RY in. And again, we want to feed through. So we want to go RS cross RX in via the identity cross W in star. And then I want to take this fixed point of phi, which will get me Rx in cross Rx out. And now I only care about my output that's stabilized, so just project onto Rx out. And then I can do my W star out, which gets me RY out. Okay. And yes, I feel like I had a better ending than that.
Yes.
If it converges
fixed point, like, or is it just like the end of a convergence?
Well, I mean, it's still a fixed point. So eventually you'll get some I and 0 such that if I input that into phi, I'm going to get back I and 0 again.
Oh, okay.
Yeah.
Got it.
But yes, you can run through it and
How do you
eventually.
know it's like converges?
So this is going to be because this is an acyclic graph, and it depends on the things prior to it.
Great. Yeah, totally.
Yeah.
Got it.
Yeah. Wait, what?
Wait, did you finish or no? Sorry.
Yeah, no, sorry, I didn't.
Questions for Keri? Discussions?
Yeah.
No,
I think you're first.
yeah, is there some continuous version of this where you get fixed points because something converges in the limit, or instead of just having it in finite steps because it's acyclic?
A limit. So we did it based just on finite, just on acyclic graphs. I'm not sure.
I think if you had cycles, I would be worried that it wouldn't converge. Like that they would just be like some like they bounce back and forth.
Yeah. But if you somehow restricted the if you restricted the dynamics to ones where you
I
have
think what's scary for me for that is like then it's like given a morphism, I can only input some of the things into the little boxes,
okay.
and it's really nice to be able to be like, you can just deal with the syntax, you know, the composition and the things you plug in separately. So it's something that I would
Yeah.
worry about.
Because I'm just thinking of like there are models in economics where actually for certain inputs that you don't converge, so they're not allowed, but it's still but if they satisfy certain conditions, then you do, and it still makes sense to talk about those. So
Cool.
yeah.
So, I mean, this is more of just like an add-on comment, not a question for that. But so, I guess presumably if you like, instead of the reals, if you did like the one-point factorification of that, where you allow infinity, and so you let things like just not converge in some cases, you might be able to tell some sort of story like that, but not sure.
Could still oscillate. Nothing.
Yeah, that's true.
So what is fundamental about R again? Like, and not just an example, like why?
So we just care about things defined on Euclidean spaces. I mean, that's how you're going to get continuity too. I mean, there might be other examples, but that's how I cannot view it as just a discrete thing as the next state. I can view it as some sort of continuous to the next state.
Oh yeah. So it's a continuous state Mealy machine, but not.
Yeah, I mean, you could view it like that, yeah.
Yeah. Okay. And then, but the tape isn't continuous though.
The tape.
You're not running in continuous time so far, right? I think that's the
Yeah,
same
that's what
question.
About what we're doing here?
Yeah.
No, but you could view it like that if you.
By like differentiating the update or something? Like
By. No, you can go. I was going to say by viewing this update function as, wait, let me think. So we want to view now the update function as a, wait, hold on, correct me if I'm wrong.
not putting a tangent vector maybe.
Yeah, exactly. So we want to say u of s equals, so we want to, I don't know if that's a good notation, but so we want to view it as a tangent vector, yeah.
Oh yeah.
Can I say the punchline to that also?
Yes.
Like the reason I am so excited about that is because we have also something instead of semantics and stock and flow diagrams, and then you have like a, I guess again semantics mapping from the stock and flow diagram into the one where it's continuous time instead of the one where it's discrete time.
I can draw it. So then we'll have D, dWd. So we have some stock flow 1, then we have the dynam, which we defined here, and we have a natural transformation between the two. Yes.
At the risk of maybe asking the dumbest question here, I'm just going to go do it. I feel like there are 3 different things that I'm tempted to picture as processes playing out over time, and I'm trying to not get the 3 of them confused. And one of them is picturing a process going on through time, following from inputs to outputs and back possibly. And that is kind of orthogonal to the indexation by the monoid of R, and that's time.
Yeah. Okay, wait.
Those
Yeah.
two, are not kind of linked yet conceptually.
Yes, but it's how you think of them. But yes.
And then, you're also kind of tempted to view there being some process playing out over time of combining them, but that's then a whole third different thing that is best to not get mixed up, right?
Wait, can you say that third one?
Oh, so just the composition of these things is then also something that I'd be tempted to picture happening in time, and that's a whole different notion of time.
No, that happens outside of time. That's
Yeah,
totally
exactly.
my God.
I don't know. Somebody go.
Okay, so how, I'm not sure I have this fully formed in my head yet, but so how in practice, if you were wanting to implement this as something you could actually build stuff with, would you check all of these conditions that you've set up on these morphisms? I assume acyclicity you can do by just doing a search on the graphs and stuff like that, but so.
Yeah, so that would be a search one, yeah.
Yeah. And then so for those other ones where each output bar only has to depend on the thing that, I guess you can just do that with some linear arithmetic or something like that.
Okay, I don't know.
Instead, you could just define all your RJs and then push them together.
That's true, yeah.
And this has been implemented by Algebra Julia.
In the proof, so your definition of the Y subcategory is like a negation. It said something is not cyclic, that there does not exist a cycle. An acyclic is like a not.
Yes, yeah.
And you're using it to construct the actual set mapping, where you add a bunch of things and you know that sum is gonna converge in how did you turn the non-existence of the cycle into the knowledge of the summation or something?
Wait, sorry.
Am I missing something?
The non-existence of a cycle becomes the positive knowledge that the graph is acyclic, right?
Right, and I guess I'm thinking when you compose the acyclicity,
Yes.
you somehow are actually composing the summing term. Like when you prove it in algebra, somehow in my mind when I'm this seems hard, when I'm I don't want to do this myself, I'm glad someone else did it. Because I'm worried about how that acyclicity turns into sums that do the right thing when you
Wait, sorry.
when you compose.
So we're saying, or is what you're saying that if I have no cycles with W and then I have no cycles in W prime, which is a G, then I don't have any cycles in their composition?
I believe that.
Okay.
But also that you turn each of those non-existences of a cycle into a positive form, into a form for a sum. Over there on the or maybe not a sum, but for
Yeah.
do a formula for
Calculating what you get in the output. And stuff
for calculating what you get in the output.
Yeah.
And so you have to take those non-existence of cycles
just
and
to
combine them.
interject a little stuff from constructive math and stuff like that. So so definitely classically, and constructively Pauli, but it also will depend on which notion of finiteness you're using. Acyclicity should be equivalent to all paths in your graph are finite.
Right. But I not only need to know that they are finite, but that those finite paths combine properly to make this an algebra, right? is that not a sticking point? Maybe it's, I mean, not that it's hard, or not that it's a sticking point or problem. I'm just like, I would think that part of the proof would be hard or something. But maybe I'm wrong.
So one thing you could do is replace the property of being acyclic with like the structure having a partial order, and then seek to combine those partial orders,
Yes.
which would probably jive well with an implementation too, where likely you're going to end up constructing such an order anyway. Like the way you would verify that it's acyclic would be to like actually do like the topological sort algorithm, which would give you one of these structures.
Okay, thanks.
Yeah.
So this is sort of like a very combinatorial way of doing this. One of the things I like about wiring diagrams is that you can think of wiring diagrams as a special case of lenses
Mhm.
in like FinSet op, which is the free Cartesian category.
Yes.
So there's sort of like a categorical story for wiring diagrams, which says like, you know, okay, there's this general story for lenses, and then wiring diagrams are free lenses. Is there sort of a general story for some kind of instantaneous lens or something?
Well,
which
yeah,
this is the
because we'd have
combinatorial-
issues with the morphisms.
Okay.
Right, because, well, I'm saying if we just took lens, because I don't want to go, one goes there, wait, actually, I see what you're saying.
Like, yeah, not necessarily lenses.
Yeah, I see.
But sort of like a semantics picture that is sort of,
That's based on that.
that's based on like categorical structure.
Yeah,
So
yeah.
you can do lenses in any Cartesian category. You can do this in any what category?
Okay, I don't know,
Okay.
but that's interesting.
If I had to guess, I would say finitely complete category, but to handle the dependencies.
I think you mean
What
exponentials.
are you doing pullbacks then?
You mean
Well,
here? I think you mean
Yeah, there's a bunch of.
What?
I think
Oh,
you mean
there's pullbacks when you compose the wiring diagram.
Yeah.
There's not necessarily pullbacks in the semantics.
Wait, I mean, we use them a lot in the sense of when we go back down and up.
Oh, I'm not talking about like pullbacks for
Wires.
real on wires. I'm talking like like she said co-complete.
Oh.
Or, sorry, finitely complete.
But yeah.
Categories. Yeah. Categorical.
So I'd be tempted to somehow find a way to represent the structure of dependencies that you have in these boxes as like some kind of bundle type of thing with like a display map, and then do that. And so that would be, and then presumably when you would be combining those, you would end up doing pullbacks to combine those in an appropriate way. But I'd have to work that out for myself, or someone else would have to work it out.
Yeah. So with your definition of cycle, can you make an incomplete wire diagram and say that if you complete the wire diagram in any other way, then it won't create a cycle?
But wait, what do we mean by
Wire diagram
incomplete?
have to be complete at that time that you're checking for cycles.
At the time, yeah, okay, so we already chose an F, so we already have all the W, W ins, W outs, and we already have the dependency D of X. So in that sense, yes, we already would know immediately if it would form a cycle.
Is that something you're interested in though? Like,
What do you mean, wait, sorry, what do you mean by incomplete?
like,
Like we only have some of the wires at that given time?
yeah, so like you've completed the wiring diagram on that one in the right of you.
Here.
Yeah, so like that's complete, but if you just like erase some of them and then like, can you somehow check the definition of cycle, or it's just
Well, that would be a different F then.
Like maybe there's a question: could you know that there's not going to turn out to be a cycle before you've even finished putting all the wires in for your F? But I think probably not.
No, I would think you would need, yeah.
you need that? Okay.
Yeah. Thank you.